All right, welcome back to the data sharing series. Today I'm going to talk about this paper we wrote about 10 years ago on epitaxial growth candidates. This is published in ACS Applied Materials Interfaces. And let me just refresh this. The goal of this paper was to use computations to find metal oxides BO2 composition like RuO2, titanium dioxide, tin oxide, etc., and look at different polymorphs like brookite, rutile, anatase, columbite, and look at where the most stable phases are. And if we could find them in this estimated window, then they are candidates for growth as epitaxial films. So the gist is we had 6 polymorphs, 5 different oxides, so that's already 30 data sets of structures at different volumes. And then we also looked at several different exchange correlation functionals, maybe at least 3. And then that led to about 100 data sets for these calculations that we stored in the supporting information file. So that was the idea. We calculated, say, rutile structure at a bunch of different volumes for RuO2, for columbite, and for anatase. Anatase is too unstable, we'll never be able to make it, but it looks like columbite is potentially stable enough and might be a target, so it might be possible to grow columbite RuO2 on the right substrate if you could find it. Okay, so it was a fun paper to work on. We used JSON to store all of this data, and we're going to look at the supporting information down here and see what we can find. So if you've been following this, you might recognize these documents. When you see enough of them, you might see like, oh, this was probably generated by LaTeX, and since it comes from our group, that probably means by 2014 it was generated from org mode. And in fact, you see the little thumbtack here that suggests there is an attachment with the data, and it says right here that data is attached as JSON. So to get this, we're going to have to go ahead and download this this PDF and use it open it in a real PDF editor. So the web browser doesn't allow you to extract attachments, but something like Adobe PDF will. And so we have 2 files, so we can save this attachment. It's going to go in downloads, so that's the JSON file we'll look at in a moment. And we'll also look at the supporting information .org file, because that is the full document that generated that, and it's probably going to have useful information, I should say. Okay, so again, you have to read these papers to understand what's the data. It's kind of like mining the data, if you want. Here is some information that says the data is stored in standard dictionary syntax in Python. So once you load the JSON file, it's like a serialized dictionary in a lot of ways. JSON's a little bit limited. It supports like the main data kinds, strings, integers, floats, lists, but it doesn't directly support an array except as a list or list of lists. And it doesn't have support for different kinds of floats or different kinds of integers for the most part, like out of the box. It's just for simple numbers, lists of numbers, strings, and you can nest these things together. So this one is pretty deeply nested. There's a oxide polymorph functional either equation of state or final, and you have to read the paper to figure out what's the difference between those. And then finally, a list of calculations that come. One of the reasons we chose JSON in here is because it is human readable. You can, and we'll do that in a moment, open it and explore it. And here you see that this hierarchy in the JSON editor online. I'm not going to use that one. I'm just going to drag it into my browser, see what happens. But you can find tools for navigating this. So, for example, TiO2, here are the polymorphs. Within anatase, here are the functionals. I guess there's 4 functionals. And then within a functional, there's an equation of state with 10 calculations, and then a final set down here. So if we drag this file into our browser, then in theory we should be able to view it. So let's go down to the downloads and try that out. So I'm just going to take it and see if I can drag it onto the browser. This is what it looks like raw. It's not very pretty, but we have a pretty print button up here in my browser, probably because I installed something that makes it do that, some extension. And so you can see there is a way to navigate this, but there's a lot of it here, and you don't want to do this as a way of extracting the data. Right? Instead, we're going to want to look at the org file and see if there's a way we can use it directly. So let's see what we can navigate to it. So this is going to be the, oh, I didn't want that one, I want the org file. This is the file that generated that PDF. You can see the attached file and a couple things that are missing. So these images are missing, they're in the PDF, but they didn't get saved with this. So we have a little bit of loss there, but not a lot. And this is an example of using the supporting information file to get some specific data. So let's open this PDF back up. So this is a script that loads that JSON and will print data for TiO2 anatase AM05 final calculations for the first one. And then there's some example output so you can see what you should get. Now it's notable that there's no parentheses on these print statements. That means that this is going to run in Python 2. And that means that probably if I try to run this, it's going to give me an error. And that's because my default Python is Python 3. And so we need to either adjust this to get Python 2 to 3, or we need to switch Pythons. So we're going to do that. We're going to try to switch Pythons, and let's see, I never remember how to do this because I don't do it very often. I want to just list what's installed. So let's do pyenv versions. So I have a bunch of Pythons installed. I just this morning installed this 2.7.18. It builds from scratch, so it takes about 5 or 10 minutes. So we're going to switch to that one. So I'm going to say pyenv local 2.7.18, and now let's just run Python here. You can see it comes as 2.718, and so maybe this is going to run now, but it doesn't. Maybe we have to do it as global. I thought that this would automatically change that. So that's still using that one. But if I run it over here, then it's using a different one. All right, I tried this enough earlier that I thought that would work. The problem is over in here, we're using a different Python, and I need to figure out how to tell it to use Python 2. All right, so let's see which Python we have here. Still doesn't do it. Maybe we'll just say Python 2 here and see if that makes it. Python 2 not found. All right, we're getting there. This is not obviously less work than modifying this. I guess we'll check out this. Okay, we just made some progress, but it's hard to tell. When I installed this 2.7.18, it's just the basic Python. It doesn't have anything like NumPy, so let's see if we can get to that, which I think we probably ought to do this. Okay, so Python, let's see if this works. -m pip install NumPy. So we'll probably have to install all the packages that we're going to need, NumPy at a minimum. And this is mostly so we don't have to modify this code any more than necessary. The JSON data is fine. We could write Python 3 code to do this as well. It just means putting parentheses around all these print statements. But I think we'll just wait, because then we would have to switch back to our Python 3. Okay. And that's probably going to output none, so this also requires some knowledge that the results are the default is a return value, and we actually want the output, and here we get it. Okay, great. So we just succeeded in running the old Python 2. We didn't change anything here. We only changed our environment to run Python 2. And now we get all of the output that we had before. We could similarly do, should be able to run this one, but we do have to modify it to results output. And this is a little bit different, so we probably also have to say like org here. and maybe raw. And then we get our table. So this is stuff that's changed maybe in org mode since 10 years ago when we wrote this. And let's try one more. This one is surely going to fail because we don't have ASE or matplotlib installed. We'll just do that. See what happens. Python 3.5 or later is required, so that's already going to be a problem. And now is a time when it makes sense to not try to do this in Python 2 because modern ASE doesn't support that, and so you'd have to know what version of ASE did support it, and then try to install an older version. That's a lot of work, I think, so I'm just going to skip that and say pyenv global system. Make sure I get back to, that's not what I wanted. .11.4 maybe. Okay, that's also not what I wanted. Let's remove .python version. All right, so now we're back to Python 3.11.4, and so for this one, I'm going to just modify it to be to use Python 3. And I think this one is also going to be a problem because I don't have a directory called images, and so let's just make one, make dir -p images /eos, and let's get our Finder open. So I'll run this one first. That should make a directory. Oh, it's in downloads. There's the images, and then there's equation of state. And now I believe we can run this one. Now I have to, let's come back up here. And we're going to just change this back to Python. No module name matplotlib. Oh. So, all right, so I need to change back to system here. And this is one of the reasons I don't love the virtual environments and all of these things. It's very tricky to get things in the right place. All right, so let's see. We do have an error that something moved. Print method. Oh. Looks like we need to make some additional directories. So this is saying images EOS TiO2 doesn't exist, and that's you can see like over here that's true, and so we need to make sure that those directories exist. It's an interesting question how this ran before. It's possible that it used to automatically make those. os.makedir. And this uses the old format string, so I'm going to modify this to make an F string. let's see if that works. Yep, just made TiO2. And then that's okay equals true. Not that one. Let's do make ders. And it's just exist okay. Okay, so now we're just making all of these files over here with some minor changes, and we can just click on one of them and open it up. Oh, this is probably not what we want actually. All right, this is another thing that's probably changed. So this is putting all of them in one image, and we probably need to say here that we want to do a plot.figure to make a new figure, and then plot.close to do it again. Okay, so let's check out this one again. Now we have a single line, and we have made our figures for different polymorphs, for different functionals, for all of these equations of state. So I'd say that's like a pretty good success. And now I bet these even show up, except that these another thing that's kind of changed is I need to maybe add AO here, and then these will show up. So what's happening in Emacs, it's seeing 4 and making the little image 4 pixels wide right here, and so it's not really showing up. Okay, so the data's here. Obviously we can read it. Either we adapt to Python 2 and see if we can get Python 2 compatible libraries, which I decided not to do, or we adapt to Python 3 and update things where behaviors have changed. Here, for example, we will have to change all of the print statements to have parentheses, and then it should generate this table from the data. It's a lot of print, so I'm not going to do it. But we are generating a lot of the tables this way. Looks like there's not that much in here otherwise. So let's see this one. We'll just modify these so that we have parentheses. And see if this runs. And then again, AO here for that. So that generates the figure, and going back to the manuscript, I remember seeing this one in there, and I think it's probably down here as well. So all of the output that we got from before is captured, and here are the relative energetics of the TiO2 polymorphs, and these all look exactly like that. Okay, so let's do just some summary notes here. We had Python 2, code had to be updated. Can't really fault us for using Python 2. That was what was available at the time. Python 3 wasn't. Data is in JSON. Easy to read in Python. And we were able to regenerate figures and tables. To Python 3. So overall, I think that this has worked pretty well. I guess there's some, let's go back to that supporting information. Going all the way back to the beginning, right? These are all of the things you need to regenerate a VASP calculation. We have in-car parameters, we have K-point setup, we have pot cars. We're not allowed to share pot cars, so we share these hashes so you can tell what's what. You have the cell positions and the atoms in their positions, so you can get out all of the positions for rerunning a calculation. You can get the outputs that we got, the stress, the volume, total energy. We included some documentation in the JSON. It's not great, but at least it says it's the data from the output. And then forces and things like that. So you can extract a lot of information out of this, and then if you want to do something different equation of state, different kind of analysis, you can, including setting up and running new calculations if that's what you want to use in some other code or even in VASP if you want. Okay, so I think this paper should get probably an A. For data sharing. It's not perfect, and A here means the data's there, you can figure out how to reuse it. You have to read the paper to figure out how to reuse it, but I think that's the only thing that makes sense. The data by itself isn't very helpful if you don't know what it's for. So you need the paper for context. And that context includes things like units, like what are the units on that energy. There's not a standard way of storing that kind of information anyway. It might be stored in a comment or a string, or not at all. Like here we converted a bunch of things to kilojoules per mole because we worked with experimentalists and that's the unit they use. They're not familiar with an EV, and 100 kilojoules is like a nice range, where 1 EV is a less nice range for things that are hard to measure, maybe, even though they're the same range. That's how it is. All right, so the thing I like about JSON is it is easy to read. It is machine readable. It is human readable, although you don't, that's like a desperation if you had to navigate this deeply nested set of data. It is good for kind of hierarchical nested data. We have things nested by functional, by Oxide, by polymorph, and then a list of calculations, and each one of those is like a dictionary of settings itself. So it was very convenient for us to generate the JSON, and it's very convenient to read the JSON, and then we could use that JSON to generate all of the figures and do all of our analysis. So that fits the bill for share the data that you used. We did not construct it after the fact. We made the JSON first, and then we did the analysis. So that means the data we shared is the data we used, and for the most part, it looks like that worked for us. And it's not the only way you could have done this. We could have put those all in CSV files, or maybe there could have been a lot of Excel sheets, but it would have been a lot of Excel sheets, like maybe 100 or something, because we had quite a lot of data sets that were stored in there. And so Excel just would not have been like as convenient for us to use, but we could have. And CSV files would also work. You could have had like 100 CSV files. But then instead of having this like dictionary syntax, you would have to have a file-based access syntax. So you'd have to generate a file name so that you knew which file to read. All right, so that's it for this one, and I'm going to be traveling for a while, so we'll probably pick this up sometime later in August and see some different kinds of data formats and some other approaches that we've taken. So hope you learned something, and